Raise your hand for no. Okay, it looked like there was more no's, so if we have time at the very end, we'll do it. But you guys have done a lot of these already, so I'm confident you know how to do them. Just be careful with those things that I mentioned. Colligative properties. They are properties defined as ones that depend only on the concentration of ions rather than the identity of the solute. So basically that's saying that sodium chloride and potassium chloride will do the exact same thing to a boiling point, even though you have sodium versus potassium. They'll change the boiling point by the same amount. Whereas calcium chloride has more elevating power than calcium or potassium chloride because it donates more ions. Does that make sense? That's just a definition thing. Okay. Boiling point and freezing point. Okay. Oh, this is the last slide, so you can do this. And then you probably want to go over. Okay, I'll do this one and give you one. I'll do the one. Okay, sweet. So colligative properties, two common ones we see are freezing point and boiling point. Adding solutes changes both of those quantities. The factors that change the boiling points and freezing points are the Van Hoff factor, so the number of ions you put in solution, the molality, and the solvents Kf or Kb. So always remember that freezing point will go down and boiling point will go up. I know there's a question on the test, probably. I don't know for sure, but yeah. Yeah, so for example, let's see, where is it? Did you write it?
No, I didn't write it.
Okay, so just conceptually really quick. So I didn't give you the equations, but you know that the equation is this. So say you solve for this, and since it's Kb, you found that the boiling point changed by 5 degrees, and say you're working with water. So if the initial boiling point of water is 100 degrees Celsius, the final would be 105 degrees Celsius. So if you want to go to Everest and boil water on the top of it, you can add salt so that it'll boil at a higher temperature, because on top of Everest, it'll actually boil like lower than this. So you can't cook your noodles as good. But if you wanted to do freezing point, like you want to go melt snow outside, that would be delta Tf equals IKF molality. And let's say you got this is equal to 10. So if the initial freezing point of water was 0 degrees, the final would be negative 10 degrees. So just know that freezing point goes down, boiling point goes up. And now, sorry, my voice is bad, but Wade has volunteered to do the Born-Haber problem. So, yeah.
Okay, so the Born-Haber problem is, Born-Haber is actually not as hard as you guys might think. It's really simple if you just think about it in kind of distinct steps. So what you're basically doing with the Born-Haber cycle is that you're creating a new, you're doing a reaction. That's all there is to it. And it's just going through each individual step in the reaction, each phase change, and each time that you make an ion. And so each time you do that, you're doing a step in that, and each time that costs or you earn energy as opposed to that. So at the end here, you have this delta H of reaction, which is the difference between the reactants and the products, which you can find by using this equation right here. This equation will save your life with the Born-Haber cycle. It is the best way to think about it. So you have delta H of reaction is equal to the delta H of sublimation plus the delta H of the bond energies plus the delta H of ionization energy plus, I'm going to come down here, the delta H of the electron affinity. We're going to explain what each of these mean in just a second. And delta H of the lattice energy. Okay, so this total right here, in each of these steps, represents one of these right here that I've talked about, that I just told you about. So what happens first in this is that you have solid sodium plus half of a mole of Cl2 gas. So what you're going to do is you're going to sublime, so go from a solid to a gas. So you're going to have the delta H of sublimation of the Na, and even if you're the Na gas, you're going to have Na gas and 1/2 of Cl2 gas. So after that, what you're going to want to do is you're going to break these bonds right here. So you have delta H of the bond energy of this chlorine. So this chlorine, instead of being Cl2, you're going to have just Cl. It's just going to be like a single atom of Cl. Just think of it like that. So state is kind of like weird. But anyways, after that, so you're going to have, then you have your ionization energy. So delta H of the ionization energy of sodium. So that's how you remove an electron from the sodium and you make it into a sodium ion. So then after that, you have the delta H of the electron affinity. And so that's how much energy that it costs, or that you gain by giving chlorine its electron. And so it likes electrons, so it's happy, and so it actually is downhill in energy, and so you release energy. And so you gain some back. And then this right here is, this big giant number right here is the lattice energy. And usually these things are very, very happy to be together in a solid, in an ionic compound. And we know that, right? Because we know that Na plus and Cl minus, they like to be together. They like to be NaCl with table salt. And so this value is the delta H of the lattice energy, and you end up getting your product right here. And so all of these steps add up. You know, some of them are positive values, some of them are negative values, and it will give you this final value right here, this delta H of reaction. And so for this particular problem, what I have asked is to use this in order to find the electron affinity. That's the one value that I didn't give you. And so basically that's the only way these problems can be asked, is either conceptually understanding what one of the steps means, or understanding or being able to isolate one of the terms and being able to find it, and that's just algebra. And so I've given you, well, the delta H of the reaction, I haven't given you that, so I will give you that real quick. It would be is equal to 410 kilojoules per mole. Okay, does that make sense to everyone? Does anyone have any questions about that? Yeah.
Can you give us the enthalpy of reaction, the total thing to this?
Yes.
And that's the lattice energy. No, that's different.
No, so the lattice energy is how much energy you gain by putting it into this right here.
So it's solid.
Right. The reaction energy is this one right here. It's the difference between reactants and products. It is the sublimation, everyone please quiet down. Sublimation and ionization energy.
So you don't have the HQ of the enthalpy of the electron affinity.
Uh-huh.
How did you find
You can solve it.
that you don't have the enthalpy of the reaction? How do you find it?
I gave it to you.
I'm gonna do one last problem with the molecular masses, because a lot of people have questions on those. So if you want to hear that, I'm gonna do that.
Yeah.
Why is chlorine half mole?
Because you only want one chlorine atom, right? So if I had, so that's another important aspect actually. Everyone pay attention to this, is that you actually have to half this value right here, because you only have half of a mole. So this right here is kilojoules per mole, right, for the bond energies of this. And so you have to take half of that, because you only have half of a mole, because you only want one atom, as opposed to two atoms. If you had a whole mole of that, you would have two atoms.
And the reason you start with half the moles is because that's standard state. Because you always want to start in standard state and chlorine comes to diatomic.
Good? Yeah. How did I get the answer of this one? Just plug them all into that, and it's just an equality. So yeah, you just have this value equals this value plus this value plus this value plus this value plus this value, and so you just subtract all of these from this side, and you get the right answer.
What's the answer?
The answer is. I actually did not write the answer down. What did you get? Okay, cool. What was it? Anyways, cool.
Okay, so I'm going to do this molecular mass problem. So these can get kind of tricky, but I have a way that I like better, and if you like this, you can use this. If you like Macedonia's way better, feel free to use that. But I don't know how to do it. So just go to the slides and look at that. Okay. So we're gonna add 12.6 grams of an unknown tertiary salt. Okay, really quick, what does tertiary gonna mean? Yeah. No, that would be quaternary, isn't this great? Yeah. Okay. Quaternary would be 4. Sorry, but it'll be easier than that. Sorry. Okay. Tertiary salt to 75 mils of water. The kV is 0.512. The boiling point changes by 1.7 degrees. What's the molar mass of the salt? Okay. So, how I like to start is just start with the equations that I know are going to apply to the problem. So, what equation am I going to write down? Yeah. So you're going to have delta T B equals I KB molality. Okay. Now I'm going to put in what I know. They give me everything but one thing. Okay, so delta T is going to be 1.7. And does it matter if I put positive? Okay. 1.7 degrees Celsius is going to equal, we said I is 3. We said KB is 0.512. We don't know the molality, that's what we're solving for. Okay, so you're going to divide away these parts so that you have molality. Okay. So, no, because 1 degree change in Kelvin is the same as 1 degree change in Celsius. Because you just add 273, so it's 1 to 1. So, good question though. So the molality I got is 1.106. Okay. Okay. Here's the tricky part. So I'm going to change this into units that I want. So what are the units of molality? No? Moles of solute divided by kilograms of solvent. That's really important to know. Okay? So I'm going to change this to N solute divided by kg solvent. Okay, so let's look and see if we have any of those things in our problem. So we don't have the moles of solute, right? No, we have the grams of solute. Okay, but we do have the volume of solution. Solvent. So how are we going to change 75 mils into kilograms? Yeah, you're actually just going to end up dividing by 1,000, but the reason is because the density of water. So the density of water is 1 gram per mil. If you guys don't know this, just familiarize yourselves with that. So if you want to change volume of water to grams of water, or mass of water, you do 75 mils times 1 gram per mil, and like you said, it ends up being 75 grams, and we want to go to kilograms, right? So we're going to do 1,000 grams in kg, and that's going to give us the 0.075, correct? Thanks. Scott.